Okay. Okay, right. So importantly, proofs are themselves just first-class objects. So, right. So we've seen that we can use check to ask coq to print the type of a particular expression, right? And we can also use check to ask what theorem a particular identifier refers to. In other words, we can check the name of a theorem and see what the statement of that theorem is proving, right? What is the statement that the proof that that theorem represents is associated with, right? So if we check plus com, we'll get the statement of the theorem. And indeed, this is actually a very convenient command, because if you ever have some theorem you want to apply, you can always check it and see what the type of the statement of that theorem is before you apply it, and see if you can actually apply it to the goal. Yes. Right. So the reason behind this is a subtle point, is that after we put the statement of the theorem with the theorem command, and then we walk through this proof script, right? And then we hit QED. What happens? So when we hit QED, coq actually defines a proof object. So this is an object, this is a witness establishing the truth of the statement that we put up at the beginning of the theorem, right? And the type of this proof object is precisely the statement of the theorem that we proved, right? So there's an analogy here in the sense that the type of a computational object tells us what we can do with that object. So for instance, if we have plus and we look at the type of plus, it has type nat arrow, nat arrow, nat. So what does this mean? You give me two natural numbers, and I'll apply plus to it, and I will give you a natural number back, right? Similarly, the statement of a theorem tells us what you can use the theorem for. It's just a much richer sort of type, right? So if we have an object of type n equals m, implies n plus n equals n plus m, and you provided an argument, some witness or proof that n equals m, it will give you a new proof back that n plus n equals n plus m, right? It's a much, you could think of it as being a much richer type of function. There's an analogy here. This is really a very deep concept, right? So it turns out that we can actually apply theorems as if they were functions, right? So okay, so let's walk through a proof script to see how this works in action, right? So here we're trying to prove commutativity of plus, right? This will be the last thing we do today. So this seems pretty straightforward, right? So sorry, commutativity of plus, yeah. So we imagine that we already have in hand this theorem that x plus y equals y plus x. And we're trying to prove this bigger theorem. So the idea here is that we should be able to use this previously proven fact to make sure, prove this larger theorem, right? So down here, if we're trying to prove this, we can introduce these things, and we're going to write with plus com. Let me actually step through this right now. See what happens. Okay. So we're going to, so I'll just note that we can check plus com, and it's going to give us a type, all the way down here. The type, this is a proof, and the type of this proof object, or the statement of this proof, is that for all n and m natural numbers, n plus m equals n plus m. So if we rewrite with this previously established fact, what do we get? Well, we're going to swap, let's see, make sure I'm swapping things correctly here. So here we're going to swap x and y plus x on the left-hand branch, right? So swap. So now we've done that swap, and now if we rewrite again, we get back to the original goal. And the reason for this is that when coq is doing rewriting, it's greedily selecting the values for these quantified variables. And so it, in the first case, it selects x for the first argument to plus com, and y plus z for the argument to the second, as a second argument to plus com. And similarly, when we do it the other way, it's going to select those arguments again, only in opposite orders. So we get back to where we started. So we're sort of hosed. Or are we? So instead of letting this rewrite tactic get to choose the variables for us, we're going to be a little bit more explicit. And we're going to tell rewrite precisely what variables to use. And how we're going to do this is in much the same way that you can partially apply a function to some arguments, right? We can apply plus to 1, and then that will give us a function that adds 1 to any argument you apply it to. We can apply this lemma statement to some concrete values and rewrite with it. So let's see what happens. Oops. So here we go. Take 2. So intros plus com. So okay, here we are. So if you look down here to the rewrite lemma, now we're going to explicitly tell coq that I want to use y for the first argument to this lemma and z for the second argument to this lemma. And now, make sure I get this right. Yep. Now, when you do the rewrite, it's going to swap the y and z at the front, as you would expect. And now we have precisely the same expression on either side of the equality, and we can apply reflexivity. So I think it's probably helpful here to check the type of plus com yz. Let's walk through this. So if we check plus com, again, sorry, this is way down here. We have for all n and m, so give me an m and n, and I'll give you a proof that m plus m equals m plus n. If we partially apply this lemma to y, we're going to get a new proof that says, give me some concrete m, and I will give you a proof that y, which now is a specific value, plus that m is equal to m plus y, the specific value. So if I take it one step further, whoop, plus com yz, now I have the statement, this equality fact, about two concrete values, in this case y and z. And if I rewrite with that, as we saw previously, I get precisely the intermediate goal I wanted, and I'm done. Okay. So the key takeaway here is that you're probably getting sort of glimpses of this already, that functions and lemmas are first-class objects in coq, and we can partially apply them, and we can manipulate them in interesting ways. And similarly, propositions are first-class objects in coq, and we can manipulate them and build them in interesting ways, programmatically, potentially. And this is one of the very powerful proving techniques and reasoning techniques that often get deployed in real coq developments. And on that note, it's already 5 o'clock, so I will delay the final section of this logic lecture until next time. Actually, if there are any questions, you can ask that now too. That's what I should have said. Yeah?
So like you're using Emacs and you're moving between the commands and you move fast when the state changes. What do you press to do that?
Are you asking about using proof general? So the question was, how do you advance the command in proof general?
Yeah, you move to the next command and the state changed.
Yeah.
That's cool. How'd you do it?
You hit Control-C, Control-N.
Control-C, Control-N?
Yeah, and proof.
Go next to it, does that?
Yeah.
Right. How'd you make those slides?
You can also go back and hit Control-C, Control-U. But proof general, I mean, not proof general. coq-IDE has similar hotkeys that should do the same thing, yeah?
Control arrows.
Control arrows, yeah. Yeah. So you can do the same thing in coq-IDE if you want.
How did you make your slides?
The slides are, these slides were built from the software foundations.
I can tell that.
Yeah.
I'm curious, how did they come out?
You would have to ask Benjamin Pierce about precisely how these things are generated.
I thought there was like a coq tool to spit out slides based for...
Oh,
Yeah, that's what it looks like.
Yeah.
There are lots of hacks involved.
Yeah. The question was, how were these slides generated? The answer was, it's very hacky. But it looks nice, so yeah. Are there any other questions? Okay, great. I look forward to seeing you tomorrow.